Good morning. This is, pardon me, this is yesterday's. So I didn't get the right, it says Thursday, but we've got to find our schedule here for There we go. I think I'm still sharing this. Yes. Sorry about that. Okay, we have today we're going to talk about unit commitment for the first part of the lecture. And then we're going to do as much as we can about transmission system. And here I'm going to make the assumption that you have some background in power systems, and particularly electrical engineering. I'm not going to go through the circuit analysis of transmission systems or power flows, how we solve them. I will go through that very quickly, actually. I'll just briefly. I'm not going to go through the entire set of slides here. But we will talk about the second half, where we talk about how to do transmission system analysis, and in one case, the linear method, sometimes called DC power flow. And we're going to end up on the topic of power system security, which is very, very important to power system operators. So by way of introduction, this is a PDF file, so I'm going to have to do this this way. Okay. Wait a minute here. Start out with the first part. Just briefly on unit commitment again, and we've told you that this is the lecture that I want you to watch. There's an example in here that we put together just to show you for various loads and things what a unit commit would look like. There's an example of here called a shutdown rule. That's actually the same thing as a priority list scheme. What are some of the constraints that you run into in unit commitment? The mathematics of unit commitment is extremely complex.
Professor Gurenberg?
What?
Can you hear me? There is a background talk. I think one of the attendants is unmute, so would you please ask everybody to mute? I think Thomas Conlin is shown as unmute, and maybe he's running something in the background.
You know, I thought, okay, I'm gonna close this for now. I'm sorry. I thought that I had. Yeah.
Thank you.
Well, I'm sorry, that's not it. Now I touch.
Sorry, it wasn't Thomas because he mute now and still the noise is there, the talk in background.
Well, I don't think it's here. I don't hear anything, but then again, I have lousy hearing these days. I'm sorry. Everybody that's shown on the list over here, except me, the microphone has a line through it. They're all muted. Is it still annoying everybody? No. Okay, well, we'll keep going. So the unit commitment, the number of combinations. So you've got to go back to some math that you may have had maybe in high school, but certainly in early years in engineering school, of the number of combinations of n things that are possible. How many ways can you arrange n things? Well, if you do that, it comes out to 2n minus 2 to the n minus 1. Think of a binary number, a number that's written in ones and zeros, and it has n bits. So how many ways can you arrange that? Well, it's 2 to the n minus 1. That's the number of ways that you could arrange it. Well, many of those combinations don't work, but how many of those is taken j at a time, of n items taken j at a time, and that's this formula here. And so if you want to look at these numbers, we have these huge numbers with enormous exponents on the power of 10, just for 24 generators. Well, the solution methods for unit commitment, as I indicated yesterday, the first ones used priority list or what we call shutdown rules. Later on, that went up to dynamic programming. Was a real breakthrough in the 1960s. A friend of mine named Chuck Pang had done the research on that when he was at Purdue University, and he wrote codes based on dynamic programming, and that was the standard until later in the 1970s, early 80s, where they developed Lagrange relaxation. That is a fairly complex method that we won't try to get into. But today, there's a code called CPLEX. It was an independent company. It's now, at least as closely as I know, it's a product of IBM. And that's now the new standard. The big ISOs in the US use CPLEX to do their unit commitment. And we'll come back to that later on in the course. So these are, and that's basically CPLEX is integer programming. So this is the dynamic programming. I'm going to ask you to read that chapter and go through it fairly carefully. And we've got some very detailed, worked out examples in there. Okay, now I'm going to give you a problem today that should be available to you. Jerem posted it yesterday. This is from, if you see tables with a 4 in front, it's chapter 4. These tables are shown below, and there's unit commitment data. Actually, it's chapter 5. Why does it say chapter? Problem 5, table 4. Okay, we'll have to figure that one out. But the point is, here's the unit data. There's 4 units, And there's a time period, it's just megawatts. So it starts at 600, goes way up to a peak of 800, drops to 700, then it goes back up to 950. And there are some minimum up and minimum down times. Now, this is one of the things that really complicates unit commitment: minimum uptime and minimum downtime. Why would there be minimum uptime and minimum downtime? And a lot of it has to do with things that are technical, and other times it's managerial. Minimum uptime or downtime may have to do with the fact that you have a generating unit that's part of, let's say, three units in one plant. And once they start the unit up, the crew that works on it has to go pay attention to other generating units. Maybe they're going to be starting up. And so the rule is, once that's up, you can't just shut it back down because the crew is busy. That's literally part of the way that worked. Minimum downtime can have similar reasons, or they like to let the unit completely cool down. So you can see some of them have a 4-hour downtime. Once it's shut down, they like to let it cool down gradually for 4 hours. So they don't want you to shut them on and off. Now, let me say this as an aside. You all know that there's a drive now to supply more energy from solar and wind. Solar and wind come and go. So there's always got to be some other form of energy. Since storage is expensive and really not to the same scale, finding a 300 or 400 megawatt storage unit, let's say 300 or 400 megawatts times 2 hours, so that'd be 800 megawatt hours. You could say, oh, we just pile up batteries and start adding the cost up. The cost gets extremely high. There's lots of work going on storage, but what is really done, instead of just storing energy, which is very expensive and technically not developed well today, you have units like generating units, conventional. Now, they can't be coal-fired units, because coal-fired units don't start up and shut down. You'll break them. That's the simple word for it. You'll end up with so much maintenance on it. So instead they use gas-fired turbine units. We used to call them peaking units. Gas-fired units that can start quickly and run up and operate for, let's say, 45 minutes, an hour, 2 hours, and then go down again if the wind is coming back up. And you have to have a large amount of this backup energy. It also tends to, whatever cost savings you think you're getting from solar and wind, you end up spending a lot of money for the backup just so that you can keep power on all the time. So that's just an aside, but in this case, to do this problem, these are the combinations down here, ABC. I have given you the combination and how much the operating cost is. Incidentally, when you see up here, you see this R with a slash through it. The first 2 editions of the textbook, we tried to not use a dollar sign. Later on, we decided that most everybody needs to see a dollar sign to think of cash. So R with a slash represents a fictitious unit of currency. At one point, somebody pointed out that R could stand for South African Rand. At least that's the unit of currency that they used for many years ago. But no, it was just a fictitious. It may have come from R being the fact that we were teaching the course at Rensselaer Polytechnic Institute, so we used an R. Anyway, just remember that R is the same as a $sign. Let's see if I can. No, I can't annotate. This isn't PowerPoint. Okay, so that's the problem. And we ask you to do a unit commitment. And so you don't have to calculate the economic dispatch for 2 units or for 3 or for 4. These are the only combinations that we're gonna use. And we have the load over here. Here, these X's simply mean you don't have enough generation to supply the load. So that amount of is done for you, and you just have to do the dynamic programming part of it. So that's the homework problem that called unit commitment problem, and that you're going to that you're going to work on. And so that I'm going to turn you loose. Watch unit commitment part 2. Let me let's see. Do I have? Let me go through part 2 just quickly here. Unit commitment by Lagrange relaxation. You can watch the video on your own. But it attempts to solve the unit commitment with a mathematical solution, and it starts out and it uses what's called a dual optimization principle. And this gets way into the math here. This is the Lagrangian for a unit commitment program, and these U variables are 1 or 0. They are 1, 0 variables. That's what makes it so hard. That's what causes you to go to a program like CPLEX, which is using integer programming, which can take this problem and solve it readily. So you've got operating cost, startup cost times U. If it's 1, then the unit is in. If it's 0, you don't count it. And then here's the load constraint. So if you only count a unit if it's got a 1, otherwise it's multiplied by 0. And so that you add these up, and they have to add up to the load. And then you rewrite this. Trying to go through this fast is kind of pointless, because it requires a lot of study and thought. But Lagrange relaxation really came out and solved unit commitment much better than dynamic programming. And then there's integer program we talk about. I wrote a program using Lagrange relaxation, and it solved a 1-week schedule. Here's what it looks like. And so this one had 11 generating units. And here's the load over here, or, in the hour, this is up to 19 hours, the beginning of the week. And you see the load is going down, and now it's starting to go up, and it reaches a peak about here, 1875, and then it starts to go down. And you can see how it commits these 2 units on, only they get dispatched more and more. The first unit stays on. That's a base load unit. It's a cheap unit, so we're going to run it all the way up. And we turn generator 3 on in hour 10 and so forth. And we could do this. Now, at some point later today or tomorrow, I'm going to go through briefly on the web page. There's what's called the Power Generation Operation and Control Labs. What these are simply computer programs. Each one has a manual to explain the program. There's data sets, and so you can use this unit commitment for some large data sets that I have in there, and you can play with it. So you can play with unit commitment, economic dispatch, the transmission functions, all of the programs in the all of the technologies in the course have computer programs that you can use. But we're not going to try and do that in this course. So I am going to close this, and you have this one on your, JREM has loaded it for you to use. So we will come back to reality here. We will see you. Now the schedule says video session starts 8:45. I can see that I've gone over by 5 minutes, and it's till 9:45. So we'll run till 9:40. I'll tell you what, I'll give you till 10. I want you to work on that dynamic programming if you can. I will come back here about 9:45 so that we can go through, and you can use the texting, not texting, chat. Okay, there it is. And so, ooh, there's the program. Here's the link for the problems. Okay, so you have that. So that's the chat file, and you can ask me some questions. So in about an hour, I'll come back and start using the chat, and then when we're pretty much ready, we'll go through that problem in detail with dynamic programming. It helps to understand the dynamic program as to how that works. Okay, so what you will see next is me getting up and leaving the office here, and you will be able to watch the first video, the part 1 video on unit commitment. If you want to watch part 2, by all means, but that it's a much deeper. This course, of course, is designed as a 1-semester graduate level course. At the University of Minnesota, it's taught as what we called a 5,000 level course, meaning the university followed the 1,000 level courses are freshman, 2,000 sophomore, 3,000 junior, 4,000 senior level, and then 5,000 are the first 2 years of graduate school, or first 3, 5,000 level courses, and then we had the very, very advanced courses, 8,000 level for people doing research. But the 5,000, and this was designed as a 5,000 level course. Many masters and PhD students would take this course in the Power Systems group that is now run by Dr. Mohan and Dr. Dople and others. Okay, we will see you in a little while. Use the chat, and I will see that on the screen when I get back. Hello, is this the pharmacy? It's Willa. What are you doing? Okay. We're going to go back to our homework problem this morning. So here's the schedule, and we're gonna cover this this unit commitment problem. Just a minute, I've got to do something else here. Okay, that's my printer going back there. So here's our unit commitment problem, and what I'm going to do is to go through the solution using the small video over here. So what we see is that there's three combinations that you are allowed: A, B, and C. A, B. Now this pen may have seen its last days here. Let's see. Come on. And there's 4 units. Unit 1, Unit 2, Unit 3, Unit 4. So what we want to do is just to put, this is sort of the state space. And so we've got the A combination. So we'll just write combination, or just COMB here. Means that unit 1 is on, unit 2 is on, 3 and 4 are off. And this one simply has the first 3 on and the last one off, and this one has them all on. Now, that's the state of the units. If you're doing dynamic programming for like 12 or 15 or 18 or 60 units, this list can just go on and on. It's a huge long list of all the combinations. And then if we're doing the solution with dynamic programming, now over here, we list hours of the day or time periods. And we list the load. Okay, so this is the load. And here it's 600 megawatts. And then it's 700. And then it peaks at 800. Pardon me, it peaks at 950 here. So I'm sorry, that's not the order of the load, is it? The load is 600, 800. And then this is 700 and 950. So it looks like this. If we just draw a diagram, we go up to 800, then we drop to 700, and then we peak at the last one up at 950. So 600, 800, 700, and 950. Now you were given the cost to operate for each combination at each level of load. So you were given a table that's 3 rows and 4 columns. That table that we gave you in the that table down here is just in order of increasing load. That's not the order of the load. The load goes 6, then 8, then 7, then 950. But this is just to show you the costs. Okay, so there's the costs on this one here. So so we're back on the sheet of paper here on the little camera. So remember that if I say that I'm at this point right here, if I say I'm at that point, actually I said let's go back to, I'm sorry. If I look at this, someplace the starting conditions are at the beginning of the first units 1, 2 are up and 3 and 4 are down. 1, 2 are up, 3 and 4 are down. Actually, I'm going to redraw this because when I did the table, I did it the opposite way. So let me redraw this now. I'm sorry. So it goes A, B, C. So this is 1, 1, 0, 0, 1, 1, 1, 0, 1, 1, 1, 1. And this is unit, and those are units 1, 2, 3, 4. Okay, 1, 2, 3, 4. So this is the start, and usually we draw the load. We draw these periods of time over here, and the load goes 600, 800, 700, 950. So we'll draw it again. 6 up to 8, back down to 7, way up to 950 and down. So 600, 800, 700, and 950. This is obviously drawn specifically for a purpose. You could say you have 4 periods of 6 hours each. That happens to have a dual peak with some sort of drop off, a little bit of 100 megawatt drop off in the middle. And oftentimes you solve unit commitment with, instead of 1 hour, 24 1 hour segments, you can solve it with 12 2-hour segments, 6 4-hour, 4 6-hour like we have here, etc. So it just means you get a lot rougher solution, but it's much faster. And if you're doing a planning study or something where you don't have to be that precise, then this works fine. So this kind of thing works just fine for that. Okay, now what I want to do is we say we're going to start, and I have the numbers. I have the dispatch numbers. So I'm going to I'm going to write down the cost, and so remember, let's see. This, we said this is 8 hours, so each of these represents 2 hours. Okay, 2 hours, 2 hours, 2 hours. So here we only wanted 8 hours, and the problem told you that these were 2 hours. So then, whatever cost we have to multiply it by 2. Okay, so I have the cost here. Is the cost to just operate those units is 6505 times 2, or 1310. And there's no, when we start out, that's it. That's the cost. But if we start at this point, and I always put this over to the left. So this is the cost if you're running with just those 2 units at 600 megawatts. Now, if you want to know what does it cost if we then during the first hour, the first thing we did is we committed this unit. Okay, we committed that unit. Now we end up with an increased cost because we have a startup, and the cost up here. And what I usually do is I put just the cost to operate, which will be 2 hours times 6649, and we'll just write that 13,298. But then I have to add the startup cost. So the nomenclature up there is that I have a number, and so this is the ED cost to run the units, And then in the bottom, it's the ED cost plus startup plus and then we're gonna say, well, what was the cheapest cost to get there? Remember that so this is the best path. Best path cost. Okay, the best path cost. So remember that we have a bunch of states combinations, and then the next hour like this, and let's say to get to this point, I know what the economic dispatch cost is, so that's the ED cost, and then I could get there this way, this way, this way, or I could shut a unit down. Let's say I had that option. There would be some startup costs in here, and then there would be the cost back here. So you have to add this cost plus any startup cost to get this cost. So again, it's the economic dispatch cost, which is on the top, plus any startup. So here would be a start. And here would be a cost here, an ED cost for the previous state. And you have to say, well, I've got to do every one of those and pick the best one. And then here is the best path, okay? Best path cost. Looks like that. So when we do this, this is the principle of dynamic programming, is that each time we look at this, we know the best path. Now, I like to always do it this way and say, well, here's the whole thing. It's got 4 states and three states, pardon me. This one, I have 4x4, and I get costs to these points, but I know the best way to go back, and so forth. And let's say that this one I don't want, because it does, and so then I get the costs going up here. I get an ED cost just to generate the power, and then I get the ED plus the start plus the best path. I get two numbers over here, and I always have an arrow, okay? And let's say from this one it might be this way. The arrow tells me the best way. When I get all the way done, let's say I'm up here, I get an arrow that takes me whatever the best path. Let's say it's this one. I get down here, and then that one maybe takes me, I'm going to draw it this way because I've already got that. So you just follow the arrows, and you follow the minimum cost path back. That's the principle of dynamic programming. It also, dynamic programming is used in part of the Lagrange relaxation solution, not integer programming. Integer programming is an entire course by itself in a good operations research department. For example, at the University of Minnesota, we have such a department, and it's actually, those courses are under mechanical engineering. But integer programming is it's a mathematical procedure. It's also an art, and the CPLEX program took a lot of experts years. It was one of these distributed companies all over the world that people were paid. They worked at home or on whatever office they had, and they contributed to it. And then they would assemble it and test it, and everybody contributed. I don't know how many people, but they achieved a very good integer programming solution. As far as I know, now this is probably 8 years old, my information. CPLEX is good enough to do a 1 week unit commitment. I'm going to come back to this solution, but what 1 week is equal to 100, let's get the number right, 168 hours. And you like to know what that's doing. If you're doing in America, the ISO does a dispatch, and they do it for 24 hours ahead. And so there they can use CPLEX readily. They can use it for 1 week. Where it gets to be very difficult, and you need different algorithms, is if you're doing 1 year. If you're doing 1 year, so how much is 1 year? Let's say we'll use 365 days. 365 times 24. Okay, so that's 8760 hours. Some programs, some planning programs might run 10 years or 20 years. Well, that might be 87600, so 87,600 hours. And they tell me that that's when CPLEX just can't take it. It's too big. It's just too big a problem. And it takes much too long and kind of bogs down and quits. But and I don't know if it'll handle a year. I really don't. It certainly handles these 168 and 24 with no difficulty. Okay, so let's come back to our problem now. So in our problem, Well, I'm gonna show you the solution here. We'll put this. Let's see here. Let's just draw it this way. What you see here is here's the states A, B, C going up like that, and here's the capacity that I get. So that's important that you draw the capacity, and it's easiest to understand, although you don't have to do it this way, but for me, it's always been easiest to put the maximum capacity at the top, then the next lowest capacity, then the next lowest capacity. And that may not always look like a nice ordered progression like this. If you were doing all combinations, okay, if I was doing all combinations, I would have 16, right? I would have 2 to the 4th power, which is 16. Now, one of those 16 is stupid. It's all units off. Well, we don't need to look at all units off as a combination because we're not going to look at zero load. Okay, we're going to assume that there's always some load to be supplied each hour of the day. But we would have 16. So we've reduced it here to 3 so that we can kind of get your hands around the problem. And this number is the dispatch cost, and this is the total cost. Notice here that I have a dispatch cost $13,298, and then right here $13,408, and it's larger because I had some startup. So from here to here, I started up the second unit number. I'm sorry, 1, 2, 3, 4. I started the 3rd unit, and here I went from 1 and 2 being on to all 4. So here I started even more. So I have a higher number in the bottom down here. Now then we go to 800. Okay, well, if we come back here, we don't have to, this A here, I can just simply say is of no interest to us during the 800 megawatts, that combination, because it doesn't supply enough load. I've got to have at least 900 or 1050. So I only have to look at these 2 points up here. And I calculated the total economic dispatch cost, and that comes off of the table. The table. This is not the table that you have, but it's the same numbers, and that comes off of this this at 700. And so there's again. This is ED. Now this one down here is ED plus start plus best path. So, and the only paths that we look at here is to go all the way down here because we start here. Okay, we're starting here. It's going to be the best path because this is 13,010. This is 13,4 and 13,8. So it's much cheaper to come down here from these 2 points here. And then we go to the 700. Now the 700, we can look at this combination again. So now I'm interested in this this combination. But the truth is that I don't want to turn any units off. So from this combination of 1, 2, 3, and 4 off, I could either turn 4 on or I could just leave it as the same combination there. And then I add, again, this bottom cost to its operating cost. There's no startup. So this is the total cost down here in the bottom. And it's much cheaper than this upper one here. So I might just as well go back to here. And then the last point has to have all 4 units on. So it's forcing us to go up here. And obviously the cheapest path then is to come back here, and back here. The dotted line, okay, the one that's crosshatched is the best path. So the best unit commitment is down here. You start out with 1 and 2 are on, and then at 800 you turn on the unit 3, and you leave that combination the same for the next period of time for the 700 megawatt, and last of all you end up with all of them on. So that's the principle of using dynamic programming. Dynamic programming, as I say, was invented. I should be a little more careful, but as I recall, and I knew this guy Chuck Pang, he worked with me when I used to work at Power Technologies. He was working there then, and I think he did that as part of his PhD thesis. That was what he developed at Purdue University, and then came to work for Power Technologies in Schenectady. And we used it, and as did most of the major operations computer companies. They would solve large unit commitment programs with dynamic programming. And as we indicated in the book, when you have 1, 2, 3, 4, 5, 6, maybe let's say up to 24 generators, 24 units. The number of possible combinations is 2 to the 24th minus 1. That's a huge, huge, huge number. Very, very, very big number. And then you want to solve it. I just happen to pick 24 units, but let's say you're gonna solve that for 168 hours for a whole week. That gets to be an enormous problem. And what we would do is, because this is ordered now from max capacity, and that just means if all of them are on, what's the sum of all the units? And then let's say this is 1, 1, 1, 1, 1, 1, and then this is a 0 over here, and it goes all the way back down to let's just say a single unit. We don't bother. That's why I have the minus. We don't bother with the 0 zeros. The max capacity, the next, and we order this by capacity. We know for what the load is going to be at every hour. It's going to go like this: 24 hours a day times 7 days. Well, then we can look at the capacity range for each hour, and we know that we only need to look at a certain range when we're doing this. As the load goes down, we may shift this range up and down. So we do that this way. There were various tricks of expanding and contracting the range of search over this huge list of combinations. One company that I worked for was Control Data Corporation. It's now Siemens here in Minneapolis. And at the time, Control Data was using very large scientific computers. I'm dating myself, but in the early days of computing, Control Data Corporation made its mark in selling very fast scientific computers. They were used in most of the big, like Lawrence Livermore, those kind of labs that did atomic energy research. They were used by engineering department, large utilities. I know that Bonneville Power had a control data computer to do their calculations. IBM did not sell a computer. If they did, it wasn't that popular. And eventually control data dominated the market for supercomputers too. Control data had a guy named Seymour Cray, and that's the guy who eventually founded a separate company called Cray Computers, still in existence. But anyway, we had these big mainframe, what we used to call mainframe computers. There still are mainframe computers, but control data doesn't build them anymore. But we had large mainframe computers, and we would try to solve these huge unit commitment programs, and they would take hours and hours of going through all the combinations just to see if it could optimize much better. And oftentimes we discovered that you could get a significantly better solution, but eventually putting, if you went 2 or 3 hours, or if you went 2 hours of calculating, I'm just throwing numbers out, you got a solution to go 10 or 12 hours of the computer pounding away on it wouldn't get you much, if anything. So there was a kind of a point of diminishing returns. That was all changed in the 1980s. I'm going to say, I should say 1980s. I should look up the earliest papers. Superseded by Lagrange relaxation, and that is covered in detail in the text and in those video lectures that you can watch. And that was the standard until really the Lagrange relaxation was the standard until sometime in the late, let's say 2006, 7, 8, 9, sometime in there, CPLEX came along and they were able to show that they could get superior, better, more consistent unit commitment solutions than Lagrange relaxation. So I'm just gonna, we'll put this on here in red. So we went from priority list. We went to dynamic programming. And let's say this is the 1960s. We went to Lagrange relaxation, which lasted from the 1980s to let's just say 2000. I'll just say 2005 roughly, and then we went to integer programming, specifically. Now there may be other products now, but this is this IBM product, CPLEX. Many of the large ISOs use CPLEX because of the quality of solutions are so good with CPLEX. Lagrange relaxation, you can say, had a long life and was adopted by many people, and it could solve very large, like a unit commitment for 10 years. It didn't go up exponentially. It would go up pretty much linearly, the amount of time. So going from 1 year's unit commitment to 10 years would take about 10 times longer. Dynamic programming, no way. And CPLEX just reaches limits with very, very large problems. At least it did back when I was actively talking to people about that. And I don't know if that's changed, but that's the situation today. CPLEX is the preferred method. Okay, so that's unit commitment, and it is just a unit commitment is let's do a quick review, and then we'll jump out of topic. Unit commitment. Schedule of unit on, off. That's it. When the generator's on and off, and it must meet load, it must meet, and we didn't talk about this much, the load plus the spinning reserve. We'll talk about this later, and I think you might know what some of that is, but it has to meet minimum uptime and downtime constraints as well. And just to finish this out, the modern ISO does what's called a day ahead calculation. I'll just call it calculation. And what it is it's a 24-hour unit commitment, and at each hour it does an optimal power flow to get the best economics, and it does security analysis. So the abbreviation has come out: security constrained unit commitment, or SCUC. You may see that abbreviation, and we'll talk about this tomorrow. And that security constrained unit commitment is this 24-hour ahead that is done by the ISO independent system operators like PJM, like MISO here where we are in the Midwest, California ISO, which eventually is going to cover the whole western part of the U.S., ERCOT in Texas, and so forth. So that's unit commitment, a very, very difficult calculation. As I say, nowadays, this entire thing is done in CPLEX, in the integer programming. All right, now, I'm gonna, let's see, we gotta change back to the other camera. And I'm going to share this. So, let's do, no, that's not it. I'm gonna stop doing this for a minute here because I gotta find my files. Let's see. here we go. One thing that we skipped, part of the book, but we skipped completely because of this has only got 3 days in the course here, was to try to cover the generation with limited supply. That would be fuel scheduling as well as hydro scheduling, where you're dealing with the fuel or water over time. And there's a set of lectures on that. Now, transmission system effects is one of the lectures, and the other one here, I'm sorry, I had all of these ready to go before, and my wonderful computer just shut down this PDF program, and so I'm having to get it all set up here now. Well, this is 10B. I don't want 10B. What happened to? Let's change the order. Let's go to 10. Okay, here we go. All right, so transmission. I'm going to go through the first part of this. It's optional for you. We're going to go through this a little bit quickly here, and then I'm going to let you do the video for the second part. This is just a map. You can see here is a city. We've got streets. And we've got a power plant here and here. We've got substations here. And the dotted lines represent, these dashed lines represent power lines. This represents a railroad and so forth. So we want you to understand.
Excuse me, we don't see your screen.
Aha, thank you.
Thank you.
Share. Thank you. Okay, now you see it. So this is the map. The roadways are the dark. The long dashed lines represent transmission lines, power plants, substations, and the dotted lines are railroads. And so we want you to understand that a power system is spread out over the countryside, over cities, over states, the entire country. And if we just look at the electrical, this is the same power system, what we call a one-line diagram. Why is it one line? And it's one line because these we represent three-phase transmission lines. I am gonna stop. I can't resist. I have a captive audience with you guys, so we're gonna show you Wallenberg. Anytime you look at map, you look at pictures, you will often see the picture of a transmission line that looks like this. It's got now what's wrong with that picture? What is wrong with that picture? What is wrong with it is that there's only two conductors, and virtually all of the systems around the world have three conductors, and we call them ABC, three-phase. You will see this kind when it's drawn by a non-electric power engineer. If it's drawn by an artist, they draw two wires because they're used to a power cord coming out of the plug, and it has two wires. You can also, of course, see this kind of tower where we have 6 wires. Well, what on earth is that? Well, what that is it's 2 circuits. So here's circuit 1 and circuit 2, but 3 wires in each one. This is very common for lines. Even in Minneapolis, surrounding the city of Minneapolis, we have a ring of 345 double circuit transmission that goes all the way around the city, and then it runs up north to and out west, and it runs down south to Rochester, and it runs north. I'm trying to think of the name of the substate, but anyway, it runs up to where that 500 kV. But this is so this is a 345 kV transmission, and so it's got, you know, it's got 6 wires, and you may actually see a wire on the top that's not on an insulator. That's connected to the tower. That's called a ground wire, and the idea is that hopefully if lightning comes down, it'll hit the ground wire and go right into the ground. When they build these towers, I talked to somebody that did this. They have a cement column that supports each leg of the tower. I'm just going to draw a couple of them here, and they have a steel structure inside there, and they poured the cement. But there's also a bolt at the top that they then bolt, and there's a cable that goes down and a ground rod that's driven down into the earth. So hopefully, if it gets hit by lightning, then it goes down through the tower and through this cable and down like that. It shorts it down to the ground, and it won't get into the phase wires. If it does, of course, then you've got arcing and you've got to open the circuit breakers. But this is what my pet peeve is, to see two conductors wires, and you'll see the tower will look like this, and it'll just have this. Now, if it's drawn like this, the steel and so forth, and there's a tower across like this, it could be DC transmission. We do have some DC transmission in Minnesota, two circuits that both go out to North Dakota. One that goes into Minnesota Power up north, and one that comes in here to Great River Energy, and it's not far from the city of Minneapolis. That could be DC. But when you see most people drawing, they like to use 2 conductors because that's all they know. It should be 3. So I always teach this in my classes. But we use what we call one-line diagrams. And I gotta share that. So one-line diagrams means that we're representing 3-phase circuit. So there's really three wires here, and there's 3 buses and so forth. So it's always 3, but we draw it as 1. Now, what we also do is we solve power flows as if it was only a single circuit. We use what's called a per unit system, which allows us to calculate as if it's a 1 circuit, but the numbers are true for 3 phase. That's called the positive sequence network diagram. Anyway, I'm not going to go into a lot of that because that's way outside of the course. This is just to show you a little about substation 1 lines. Okay, breakers, buses. These are called disconnect switches. If you're going to work on the breaker, you open the breaker so there's no current flowing through it, and then you open these switches, and the idea is that this gives you a big gap, and now this device, this circuit breaker, is protected because there's big air gaps on each side where they open the disconnect switches, and then they take a chain or a cable, bolt it on, and bolt it to ground. Now it's safe to let the people go in and work on it. It's grounded. So that's what these switches are. They're called disconnect switches. And so this is a single bus. This is a sectionalized bus. I can open this breaker and I create two buses. This is a thing called a main and transfer bus. There's the main bus here, and then I can transfer circuits. If I lose a breaker, I can transfer it over to this breaker and let this breaker work. This is one that's called a ring bus. You'll notice that there's a breaker, and there's a transmission line on it, then there's a breaker, and then there's a bus section with a transmission line, a breaker, and so forth. This is called a ring bus. Any of you that are living in Minneapolis, if you end up going up 494, just north of where I live in Minnetonka, you pass what's called the Parkers Lake substation. It's on the east side of 494. It's a big ring bus. Breaker and a half scheme. Notice how much more complicated this gets. And this is double breaker, double bus. These are combinations. Now here's the point. When we do analysis in the operations area, we have to account for the breakers that are open or closed. If all the breakers here are closed, then these two transformers and these two transmission lines are both connected to the same bus like that. But if we have open breakers, these ones that are crosshatched are open, then it creates two buses. There's actually two buses. And so the topology, that's what we just call the processor, the topology processing. This is the bus branch one line model. And I'm gonna skip through a lot of this because this is AC power flow theory. The power is S, which is the MVA. This is megawatts, megavars here. The Q is the reactive power. It's equal to the voltage at the bus. This is per unit system times the conjugate of the current. And if you write that all out, you get this. You get this, whereas this is the sine and cosine. These are the phase angle between that's represented by the impedance. These are the bus phase angles, I and J. And we do a solution that's called the Newton power flow. It's Newton's method where we have to take all those nonlinear equations and take the first derivative and build a matrix. Let's see if we got the matrix. Here is the transmission line model. Virtually all of the world, we use the same. We use a resistor, an inductor in series, and then we have impedance to ground, and it normally would be a capacitor in here. It could be a capacitor plus a conductor. This is the model of what's called an off-nominal transformer. I'm not going to do anything with DC, but here's an example of a small system, 6 buses that we used many times in the text. And here's the power flow. What do we need for the data? We need the P and Q load on the load buses. We need the generator data, how much each generator is putting out, except for the reference bus. There's one bus that takes up all the slack of the low losses and so forth. And we know that we need to know the generation voltage schedule. This is in per unit, and the Q, the reactive limits on the generators. And then the branch data has a from bus, a to bus, an R, and X, and this B represents the impedance to ground. Generally, this can be divided by 2. It's actually the total impedance for the line. And so here's when we start the Newton power flow. We take 3 iterations, and you notice that this is converging. This represents the error. We come down here to 0.001, 0.002, and we have a very quick solution for that system. Let's see, and here it is on all the generators. And here, for example, here's bus 1. I don't have this drawn on a diagram, but bus 1, there's the actual voltage on it, the phase angle, that's the reference bus. It's putting out 228 megawatts and it's absorbing 32 megavars, and it's putting 123 megawatts and minus 35 vars. That's the flow to the branch 2, to bus 2, and to bus 5. It's got this flow. So you've got all these different flows. And this represents that it's over the upper limit for that flow. So it flags that there. So that's the process. Now, power flows are used by the hundreds of thousands. The people planning the system, they put a new line in. So they calculate the impedance, they put it in, and they try it, let's say at the system peak level during the planning process, and that would be the they would look at the results. So did this new branch cause any problems, and can I now load the system heavier with the new branch in? And if it doesn't pass everything, we try something different. If it passes everything, then we start doing outage analysis, and outage analysis simply says we take one line at a time out. So that's the power flows, and they are run over and over again by system planners. They are run as the same purpose, but for the contingency studies. The guys doing the operations are not studying additions of new equipment. That's not their job. Their job is to take the system that's given and operate it properly. Now, one of the functions that the operators need to do with the power flow is they get a call from somebody that says, you know, that transformer, we need to get in there and do some maintenance. We'd like to do that this afternoon from 1 o'clock until 6 p.m. The people in the operations office have to okay that. And what they will do is they'll say, okay, the peak load this afternoon, the best we can figure out is going to be so much. And they know how much power they're buying and selling over the system in the afternoon, and they set that up on the power flow and they run it, and to see, is it safe, just steady state all by itself with that branch or that transformer out. Now try doing it with contingencies. Take one line out in addition to the branch that's out for, or the transformer out for maintenance, and they study it to see if it's safe. So that's the security analysis that they have to do. Again, that's done with this power flow. The next one, I'm gonna let you watch the lecture. I just wanted to do the first lecture really fast, and so this is the the main thing here is to talk about the different power flow methods, a little bit of transmission losses, and so forth. Now I have one assignment for homework for you that you can do as part of you're supposed to be doing the video lecture from 11. I took 13 minutes of that away from you, but I'm going to give you, let's see, this is, okay, I've got to load. Let's see. So here's a problem that you're going to work on this afternoon. You're given a 4-bus system that looks like this. And it's got a reference bus, and then it's got three buses, 3 generators, and 1 load. And there's the data. And we just, in this linear method, we just use X. So the whole transmission line, you throw out the capacitance to ground, you throw out the resistance, and it's all done with X. This is often called DC because the theory says I can solve power flows with just phase angle, no voltage magnitude. So I actually have a linear power flow. Build the B sub X matrix. This is part of your lecture. And then talks about how to set it up so you can invert it. And then what we want you to do is to solve all the power flows in that using the DC or linear power flow. That's going to take you a while, so I'm going to give you the rest of the video session. It goes from 11 to 12, and I'm going to ruin your lunch break by having you continue to work on that problem during lunch, okay? So that should be, oh. J-Ram, I'm gonna, I need to send this to you, right? So that they can have it. I'm sorry. He's not there. I will send him that in an email. Somebody's gonna have to wake him up and we'll get him online here. Okay, so I will send that file to him, and we will see you all. You're going to do the lecture, which is called Transmission System Effects. It's actually called 10B, Module 10B, or Part 2. Okay. Okay, welcome back. Um, we're going to look at this this problem using the linear power flow, and I'm going to do most of it on the small screen over here. I will go through this problem. This method, let me say this. This method of linear power flow or DC power flow analysis is still widely used. For the most part, when they are doing contingency or security constrained unit commitment, they are using this method. They do use real power flows, AC power flows, in doing planning studies and in doing contingency analysis in operation systems. But excuse me, this has been the summer of allergies for me. AC is necessary. Let's get the screen up going here and let's see, where am I? Here we are. So AC power flow. So we get voltage magnitude, which is in an AC system, you always designate it as an absolute value because it's a vector. We get the phase angles, which are incidental to the calculation. We get P flow and Q flow. We get P generated, Q generated, etc. And we also get P losses and Q losses. So there's a lot of things going on with an AC power flow, but it's a big calculation. It takes time. When I was a youth, back in the 70s, about 40 years ago, I did a lot of work on how to make the AC method fast, how to select contingencies in AC really fast. And they were used by a lot of people. But I recently met a student, or met with a bunch of students of mine that work at Siemens, and I asked them if they're still using that, and they said, nah. I said, no, and he said, no. We need fast answers. And yet they want to study thousands of outage cases. So how do you do that? Well, it turns out that the hardware of computing hardware has gained so much that on a single board they can get a good processor, and they can get 32 GB of memory or something like that, and then they just have a fast bus that they can transfer stuff to the main processor. And so if they want to study a lot of power flows, they put in 10 or 20 boards, and they just say, okay, we're going to do the first, we're going to divide the number of contingencies up. So suppose I want to do 1,000 power flows. Well, if I have 10 boards, I can do 100 contingency studies on each board. Now you're getting to the point where they can get it done in a couple minutes, which is what they need. So today they just use big word multi, processing, meaning more processors. I don't mean cores like you'd find in an Intel processor, Core 5, Core 7. I mean complete boards, complete memory, and they all run independently. So each board gets an assignment, and off it goes by itself, and then it returns its own answers back over a network. The DC or linear power flow is very fast, but you only get the phase angles, and you get the P generated, and you get the P flow. So there's no voltage magnitude, no Q gen or Q flow, and there's no P loss or Q loss. So you miss that on the DC, but it's fast. And it is linear, and that means that you can formulate the problem, and it's still used in planning studies, and it's used in the security constrained optimal power flow, which is what the ISO has inside of the security constrained unit commitment. Okay, remember I said that the unit commitment has an optimal power flow for each hour. That's what you use to do the dispatching. So it does a security constrained UC, SCUC. But they would still use, many of them still would use the DC method. Okay. So that's why this problem, that's why I gave you this problem, because it is very important to still to understand the linear method. Now the basis of the linear method is as follows. Here's a transmission line. It has a phase angle I and a phase angle J. Now what we say is, we say voltage, I'm going off the paper here. Voltage magnitudes are all approximately 1.0. Of course, they're close, but they're not all exactly 1.0. And we're saying that the phase angle I minus phase angle J across transmission lines is small. And and we're also having some other discussions sometimes about the magnitude of the resistance and so forth. But with those assumptions, we can say, given if we can just get rid of the AC effects altogether, and we say that power flow P, this is Pi to J, is simply equal to 1 over Xij. This is X is the inductive reactance times theta I minus theta J. Linear equation. There's no sines, cosines. There's no squares. This is if you were doing this with DC, with a DC circuit. So DC circuit like this, where you had V1 and V2 DC, well then the current Ij, or 1 to 2, let's say here, is equal to 1 over R, this is R, times V1 minus V2. That would be taught to you in the first few weeks of a course on circuit analysis. And so this is a linear equation. Now, if I then want to to solve a circuit like this. One, two, three. Well, I have to form a set of equations. What we're going to say, well, this is P-gen here, and we have P load 2 and P load 3, and these have to add up to the gen. There's no losses, so whatever this generates, that's the sum of these two loads. But how does the flows go? And that's what we'd like to do, and that's what this problem is all about. And the first thing that we do is we say, well, okay, P-gen, or let's say up here we call this P1, and we'll call this P2 and P3. But we're gonna draw them each as if they're going in, and that's the nomenclature that we're going to use. So P1 is equal to P12 plus, get out of here, I gotta, P3 plus P13. P2 is P2 to 1 plus P2 to 3. P3 is P31 plus P32. Okay, well that we can write these equations now. P12 is 1 over R1, 1 over X12 theta 1 minus theta 2. This is equal to 1 over X. Also, this is 2 to 3, so 2, 3, theta 2 minus theta 3. And this is equal to, I'm sorry, I'm just doing the first terms in here. 1 over X 3, 1, or 1, 3, theta 3 minus theta 1. So the last part, the other term here is P13, so it's 1 over X13, theta 1 minus theta 3, plus 1 over X 2, 3, theta 2 minus theta 3, plus 1 over X. That's this term 3, 2, that's 2, 3. I like to write the smaller index first, but we got to get the thetas in the right order. So this is 3 minus theta 2. Right now, it turns out that I can set this up as a 3. Notice that there's 3. These are known. They're known values, and we need to find theta 1, theta 2, and theta 3. Now, the problem with this, the one difficulty, you can't solve those linear equations because they're linearly dependent on each other, and all that means is if I form the matrix, it's singular. You cannot invert it. So I'm going to set up the matrix, and then I'm going to show the trick that is very easy to learn. So I'm going to say that this is a matrix. It says P1, P2, P3 is equal to this matrix times theta 1, theta 2, theta 3. And what do I have times up here times theta 1? Well, I have 1 over, pardon me, x1 plus 1 over x 1, 2, and 1, 3. Then I have minus 1 over x12 and minus 1 over x13. And you'll see a pattern here, you should anyway. So on 2, this in here we get 1 over x23 plus 1 over x, wait a minute here, 2, this should be 2, 1. And this should be 2 minus 1. This is 1 over, so I'm looking at the 2 is x23, a 2, 1, 2, 1, and 2, 3. And then this is minus 1 over x12 and minus 1 over x2, 3. And then this one turns out to be minus 1 over x1, 3, minus 1 over x2, 3, and 1 over x1, 3, plus 1 over x 2, 3. If you've ever done, and you should have done this, if you're an electrical engineer, you would have done solutions like this. If you were doing it with impedances, you would call it an impedance matrix. Pardon me, you'd call this an admittance matrix. So it looks like a Y, an admittance matrix. So what we want to do now is talk about this. If I start adding columns to each other here, what's going to happen is that I can eliminate one of the rows completely. These two rows linear. If I add them together right, I can equal this other row. So I can subtract, and that means that it's a singular matrix. You cannot invert it. Well, what we do know, however, and the way that you solve this, and I'm going to do it the following way, is I'm going to say, well, I'm going to say that generally one bus has fixed theta equal to 0. Fixed theta equal to 0, and then you solve for the other two. Now that's called the reference bus or swing bus in the system when they do very large power flows. And power flows are routinely done for the entire eastern interconnection of the United States, meaning it goes from New England all the way down to Mississippi, and all the way actually over into part of the West. The western region of the U.S. is separated from the eastern by DC-DC interconnections across them. So they don't solve the AC as one, or they could, but they generally don't. So if you're solving this 25, 30,000 bus power flow, you need a reference bus. And so they use one of the biggest generators they can. Often it's a big generating plant in Tennessee Valley Authority, a huge coal plant down there at near Chattanooga, for example. Or it can be any place. It can be any place in the country, the reference bus. So it's generally the reference bus, called the reference bus. All right, so if I were to take this example, I would say, okay, so remember we've got, and here I just do I didn't draw the lines for so here we've got a load, and there we've got a load. I remember I said when I analyzed it that this was P1, and that's P2, and that's P3. Well, this one we're gonna set theta 1 equal to 0. So the easiest thing to do then is to do it like this and say, all right, if I know the phase angle on number 1 is 0, then I need to solve for theta 2 and theta 3. And I say, well, P1, I don't care. So I'm just going to put a 0 in here for now, but that's just a placeholder. Here's P2, P3. And so you put zeros in the rows and columns like this. And now you have a 2 by 2 matrix that can be inverted. And that 2 by 2 matrix is got 1 over x21 plus 1 over x23 minus 1 over x23 minus 1 over x23, and then 1 over x13 plus 1 over x23. So there's this matrix. Now, there's simple formulas for finding the inverse of that matrix. And so we're gonna, this is called B sub x. And so then if I want to solve, remember this is P1, P2, P3. We don't really, and 0, theta 2, theta 3. So at this point, I want to say, okay, I want to solve for theta 2 and theta 3 equals, and I want to invert this really. Well, when you have the 0 rows and so forth, the thing you do is you put a 1 up here because it doesn't, it just carries over. It says 0 equals 0. And now you put the B sub x matrix inverse in here. That would be the inverse like that. So you really only have to invert the 2 by 2. And then over here we have P1, P2, P3. Okay. And then you can just solve it and you get theta 2 and theta 3. That's all you need. Now, I want to point out that at a bus, if there's power going into the bus, at P1, for example, then P1 is a generator and it's positive. But at P2, we said, well, this is P2, but it's really a load coming out here. PL2 is coming out. So we say P2 is equal to minus PL2, meaning it's negative, it's coming out of the bus. Same thing for P3. The mathematics is always based on a power going into the bus, but if it's a load bus, then that power P3 is negative PL3. So this would equal minus PL2, and this one would equal minus PL3. And that's the basis of the solution that we're gonna do. And I realize that I don't know if you guys, if you had access to MATLAB, that's what us academics use all the time. And if you're an engineer, I highly recommend MATLAB. But you can do matrix inverting on any Excel spreadsheet. It's a little bit difficult to set up. I found it difficult to set up, but you could do that. So you could, and I've done problems. If you go through any of the problem sets that are on the CUSP website, when you get to these linear solutions, you'll find me using spreadsheets. So the B sub x matrix for our 5-bus system, and where I am gonna let's see. Here's our problem right here. So if we're going to solve that, it's 1, 2, 3, 4. Now I've numbered it. P1, P2. These are powers entering. Okay, here's P1, P2, and this is a load, but this is the definition of P3, and this is PL3. So P3 equals minus PL3, and P4 again is a power going in P4, but it's really coming out PL4. So P4 equals minus PL4, and we've got transmission lines that look like this. Okay. So if we want to do here's the impedances. So let's take x12 is 0.2. So 1 over x12. We're always dealing with the inverses is 5, right? x14 is 0.4. So 1 over x14 is 2.5. x13 equals 0.25. So 1 over x13 is 4. And x24 equals 0.5. So 1 over x24 equals 2. And x34 equals 0.1. 1 over x34 equals 10. That's no surprise. I engineered the problem so we'd have nice round numbers like that. And so now we build the matrix. And the definition of this B sub x matrix, okay? The diagonal term.
Professor?
Yes.
Are you trying to show your test sheet or the screen of your computer?
Do you see this?
I can see the exercises.
I'm sorry. I wanted you to see.
It makes all this stuff.
This you missed.
Everything, yeah, most.
I'm sorry. This Zoom thing. If I ever suggested something to them that it would be nice to have. See here, I have a little window that shows me what's coming on here, but when I'm doing the share, it takes the whole screen, and I'm not sure what you're seeing. They have a pretty good product here, but it needs to improve.
Now I can see your worksheet.
Yeah, but I'll go over it again. I'll just talk about these. There's the diagram that was on the screen before. And the point is that P1 is equal to the generation here at generator 1. P2 is in, it's positive. So let's say P1 is equal to P gen 1. P2 is P gen 2. P3, again, the definition of P3 is an injection into the bus, and that will equal the negative of the load on 3. P4 will equal the negative of the load at 4 because that's power coming out. So all we're saying is power coming out is negative of power going in. Very, very simple. These are the impedances, 2, 0.2, 0.4, etc. And I'm going to invert those numbers and get 5, 2.5, 4, 2, and 10. Okay? So the diagonal term at I is equal to the sum of the 1 over xij for j equal to 1 to n. Now that means all the buses. So I sum over, at bus I sum over all the lines. You really sum over all lines connected to I. So that means J, actually this formula is, anyway, if J equals I, there is no IJ, but we're forming, and this is the term BXII. The off-diagonal term BXIJ is minus 1 over XIJ. And that's the same rules that you would use in regular circuit analysis to form an admittance matrix. It's the same rules. So we'll look up here at this matrix, And let's do bx11. So it's going to have all the terms connected to 1, which is 1 to 2, 1 to 3, and 1 to 4. It actually goes all three. So it's got 1 over x 1, 2, so it's got 5 plus. It's got a connection to 3, 1, 3, so it's got 4. And then it's got a connection over to 4, which is 1 to 4 is 2.5. So that's 11.5. So this number is 11.5. Now, bx12 is minus 1 over x12. Well, the x12 is 5, so this is minus 5. The x13 is minus 4 and minus 2.5. Now notice this number on the diagonal is the negative of the sum of all the other terms, the off-diagonal terms. Okay, and so this matrix then looks like this, and it is symmetric. So I know what the terms are in this column. They're the same as the terms in that row. This becomes 7. Now, this is the second bus, which is over here, does not connect directly to 3. So there's a 0 here. And this is 2. So these are the minus 2. So there's, and this is 0 and minus 2. This is 14 and minus 10, minus 10. And then last of all, 14.5. So the diagonal terms are always positive, and they are the sum of the off-diagonal terms. So this is 2.5 here. But the problem again, this is a singular matrix. You can't invert it. I don't know what happens in a spreadsheet. I'm assuming that you get some sort of error message if you tell it to invert that. So what we do, we say the reference phase angle is, this is the reference bus is, and now I'm gonna switch back to the share again. And we said this is the reference bus down here. Actually, that's a generator. What am I'm drawing a load at that bus, and here I'm not looking at that. This isn't a load. This is a generator, isn't it? So it's P4 is just equal to P gen 4. So there's our reference bus. So we're gonna make the fourth bus look like it's got 0 on it. I'm trying to set this up so you can see part of this page. And now I gotta switch back, stop sharing. There we go, for a little while anyway. So now I'm gonna say, okay, I put a 1 here and I put zeros here. Meaning I just zero them out because theta 4 will equal 0. I don't know what theta 1, 2, or 3 are. So these numbers are the same, 11.5 minus 5, minus 4, minus 5, 7, 0, minus 4, 0, 14. Now notice when I did that, the diagonals don't sum anymore, but this matrix can be inverted. That matrix is not singular, and it can be inverted. And when I invert it, I'm going to just show you this. I like to give credit. This solution to this problem was solved by a brilliant student of mine named Marcel Pozo, who last I knew was still working in Minnesota. He's from Ecuador. Brilliant guy, and so we're gonna look at this this solution So here's my B sub x matrix. And there it is when I took the zero, put a 1 in the diagonal, and then I inverted the 3 by 3. And there's the inverse. Now, I want to say something. We never actually form the inverse of a matrix in power system analysis. We don't need to. What we do is we want to solve. And if you have a set of equations and you have a matrix, you don't want to invert the matrix. That's a lot of work to get the inverse. And what you do is you take this matrix up here. So you got 11.5 minus 5 minus 4 minus 5, 7, 0, minus 4, 0, 14. I'm just going to take it in that order. So the first thing you do, and remember you have the thetas on this side and you have the p vector on this side. So we got to go back and look at the problem again. Where are we? The problem says that there's the generation, 100. Now, this is megawatts, so in per unit, this is, you divide by the base, so this is 1, 1.5, and 3.5. Okay, so we're gonna mess around with this thing. We're gonna make this a 1. And then this becomes minus 5 over 11.5 minus 4 over 11.5. And this becomes 1 over 11.5. You divide that through, so I get a 1. And now I multiply this row, the first row times 5, and subtract it so that I get a 0 here. And I get something in here, and I get something in here, and I get a different term in here. I'm not going to put the numbers. And then I do the same thing, so I get a 0 here, and I get numbers like this. Then I take this number and I convert 1, whatever that is. These are just placeholders here. And I get 0 and I get a 1 here and I get something here.
Excuse me, Professor, we're still not seeing your work.
Oh, I'm just horrible at this today. Here we go. I'm sorry. I started writing on this. All right, so let's go back. We take the matrix and we put it over here. As soon as you can't see something, yell at me, okay? I'm sorry. Here's the P, 1, 2, 1.5 and 3.5. Here's the matrix. That's just terms out of here, 3 by 3. I want to get a 1 in the upper, in the 1, 1 diagonal term. This is called triangularization. So I divide by 11.5, so I get a 1. I divide everything else by 11.5. And then I take that and I multiply it by minus 5 so that I can make this term 0, and that alters these terms. And then I multiply by 4 and add it, so I get a 0 here, and that alters these terms. Then I do the same thing down here to this term so that I get 1, 0, and I get a 1 there. This is still 0, and I make this one a 0, and I get terms like this. Last of all, I end up with numbers like this, 0, 1. These are all non-zero. This is 1 over whatever. 0, 0, like that. And then I make this into a 1. Now, once you've got this in this form, then I have a number here that says this number is equal to 1 times theta 3. So now I know the value of theta 3. Then I go to the next and I move back up, called back substitution. And by the second row now, it says I've got 1 times theta 2 plus some number times theta 3, but I just calculated it, so I can substitute and subtract, and I can solve for theta 2. Then I can do that, I can solve. So the first thing we did was we triangularized this, we altered these, and then we solved for theta 3, then theta 2, then theta 1, we already know that theta 4 is a 0. And so we just solve it that way. Now, okay, I'm going to switch back to, no, I don't have to, well, yeah, I'd rather kind of, I'd rather switch back here and show you the, where is my, oh, this is the problem solution. So there is the doing an actual inverse. Okay, and when I have that inverse, I now set up the equations. Oh, this is, the third bus is a load. So I should have put a minus 3.5. That's okay. We'll show you that in a minute. So the solution is to put the X, and we say that X, this is X. You can just put a thing like that, X matrix there. And solve for the thetas, and there are the values of theta. And they're in radians, okay? The entire, all the equations are in radians. Remember, this is the function for the power flow on that bus, Pij. And then when I get all done, and what I'm going to do here, I'm going to go back to the paper, but I'm going to turn off this so that you can see the screen. So now we'll draw this like this: generator, load, and there's a generator here. And let's see, one. So we're going to do all of these. This is 1.0. This is per unit. This is 1.5. This is 3.5 load. So we say if it's going this way, it's minus 3.5. And this thing is the reference bus. Now we're going to have to calculate that. He doesn't. He didn't do that. Marcel, you don't get a perfect grade. Whatever. He took this course about 10 years ago. In any event, the P12, so here's 1, 2, 3, 4. So this has got a flow of minus, so it's really minus 0.8, which means it's really going this way, 0.8459. The flow, the next flow is what, 1 to 3 is positive, 1.45, and 1 to 4 is 0.394 something. I'm just going to do two or three places. And then 2 to 4, 0.65, 3 to 4 is negative. So I'm going to draw 3 to 4 is minus 2. Let's just do it, minus 2.04. Or really it says that it's 2.04 going that way. So we should check, but let's look at bus number 1. P1 has a generation of 1.0, and that's equal to the flow 1.45. That's this flow here, plus 0.394 minus 0.846, really. minus 0.846. Well, this is about 0.4, so this is about 1.85, and this is about minus 0.85, so that's equal to 1.0. So that's correct. So these flows add up correctly. Let's look at P4 is equal to 0.65 is coming in, so that's minus 65 minus 0.394, and then there's 2.04 coming out. These are going to add up to essentially minus 1.04. So this is equal to plus 1.0. So let's see. This is a generation of 1, 1.0, 1.5, and this is 1.0 that we just calculated. So there's 3.5, and by golly, that's what the load is. So there's no losses in the system. And so you can quickly, very quickly, one matrix invert or triangularization, forward back substitution, very, very fast. If you use a tool like MATLAB, you know that you can invert matrices. It can take a long time. Or you can simply tell it to solve a set of linear equations. And believe me, it's not going to use matrix inversion. It's going to use triangularization to solve the set of linear equations. It's very, very fast. So that's the idea. So again, this solution is fast. And what you're going to see on the two, and I'm going to ask you, let's get to the let's get. No, what I want to do here is. Let's when you're doing the so you've done this part over the lunchtime break, and we've just done this power flow solution, this DC or linear power flow solution. I really want you to do both of these. They're fairly short. Forget that this says optional, okay? Forget that says optional. I thought this thing, this thing, now this thing says that I can annotate this. So let's see, forget that this says optional. I hope that doesn't mark that up permanently. Let's see. So mouse. If I then go to this and come back, it's as if you drew the red lines on the glass. Okay. If you've ever been in a lecture room, this happened. There was a screen that you pulled down in one of the lecture rooms on my floor at the University of Minnesota, and somebody had been giving a PowerPoint and they wanted to talk about something. They went up with a marker and they marked it on the screen. Well, the screen, instead of marking it in the computer, they marked it physically on the screen. And that little mark, I think it was with a green pen, was there forever. This is the same thing. It puts it on the glass. So I don't know.
You can on the left, at the bottom one where this pencil, maybe there must be an eraser there or somewhere.
Well, this has a clear, clear all drawings, I guess. And anyway, we will clear this.
Remain on your computer screen.
Yeah, right on my glass of my computer here. Anyway, I would like you to do both of them. They're not too long. If I've got these, where are they here? Linear. I've got them. I'm gonna here's this this one here, power system security 11A and 11B. They're each the one is only 19 pages and the other one is 15. So that's 20. That's almost 30 pages. But I want you to see them both, especially part 2. This one on part 1. And so you should watch both videos for that. We got plenty of time because if we start you right here just a little before 2, and then I will be putting a problem up. Oh, do I have the problem? I don't have the problem up, or do I? We did the linear. Let me see if I've got a problem for you. I don't think so. No. I'm going to put the problem up, and maybe about 2:30 or so. We'll give you a chance to watch at least part 1. About 2:30, I will show you the problem, and we'll let you work on it till about 3:15 or so. So that gives you an hour and a quarter, even to 3:30, and then we can go through the problem. Okay, so I'll put the problem up about 2:30, and you'll hear my voice coming through. Otherwise, I'm going to. I have a question, people. What happens when? What do you see? I'm going to blank this out. Then you can talk back to me. Okay, I'm back. So I turned off the mic. I turned off the camera. Do you just see a blank screen? Yes. I see yes at 1:53. Okay. Yes. Okay. That's just in case I get a phone call and I have to, answer it. You don't hear me talking to whoever here. My wife is upstairs, and who knows what kind of embarrassing thing I might be talking to her about spending money or whatever. Anyway, I'll be turning them off. But 2:30 or so, I'll come back for 10 minutes and explain the security analysis problem. But it's going to be based on this linear power flow, and there's a very, very nice, because it's linear, we can do some tricks with linear analysis that have been known for I would say since the 60s, late 60s. These tricks have been known, maybe even before, as far as I know. But so that's 50 years ago. Somebody worked them out, and the fact that we have them in our book it doesn't mean that we invented anything. They were all done by others back in the 50s, and they have been in wide scale use of linear contingency analysis using what are called line outage distribution factors. So we'll come back to that around 2:30 or so. So I'm going to let you all go right now. And if there's any questions, hit me with a text. I can still see the texts. Okay. Okay, people, I'm going to show you the problem, and then I will have Jairam post it for you. So here is the here is the problem. We have a bus, we have a 4-bus system. Actually, it's the same topology, although the rest of the problem's different than the one that we did before. Different impedances, and we put some limits on the flows. It's just problem 7.2 in the text. Here's the base transmission loading. Now, we don't ask you to solve a power flow. I did that for you. And there's the base loading, and you notice nothing is near the upper or lower limit. So the flow limits on the first 2 lines are 35 megawatt. The next line is 25. Then we have one that can take 40 megawatts, and then the last one is 25. So technically, the flow can be between plus and minus the limit, meaning the flow is going to burn the line down regardless of what direction it's going. If it's over the limit, it's going to heat the line up and burn it down. So technically, if you have a limit on the line flow, I've never seen it used where it's different one direction than the other. You could have things like that if it were for stability studies, but I'm not even going to go into that. Okay, we have some factors called LODF, line outage distribution factors, and power transfer distribution factors. Let me go to the, well, actually, no, I need to, let's see. While I'm here, all I have to do is, I think that's in the lecture. Okay, that's the first lecture. Here's B. Okay, power transfer distribution. And I'm going to write this on the sheet, and then I'm going to go over to the sheet. PTDF from I to JL is delta FL over delta PIJ. And okay, let's go over to my sheet now, and we will change camera. And here are those 2 formulas. We have the PTDF, and this power transfer distribution factor. And what this does, let me kind of draw. Here's a power system down here. Buses all over the place. I want to transfer power from one bus to another, and they can be way across the system. They can be hundreds of miles away. So here's I, and here's J, and I'm going to put a delta PI in here, and I'm going to take that same power out, delta P down here. Let's forget the subscript, just delta P. So I'm going to put so many megawatts in here, and I'm going to take it out down there. And what we'd like to know is, here's the flow on line L. What is the change in flow? What's the delta flow on line L? So for example, let's say this PTDF I to J on line L might be, for example, 0.15. What that says is that if I put some power in here and take it out there, this thing will change by 0.15 times whatever this power is. So for example, if this is equal to 100 megawatts, so I'm going to make a sale of 100 megawatts. I'm going to sell power here, and this guy is going to draw it out of the system. How much is it going to affect the loading on this line? And it says that the delta will equal, so the delta flow L, if you take that formula, will equal PTDF IJL times delta P IJ. So this is 100 and this is 0.15. Okay, so then this is 15 megawatts. So of the 100, 15 of that 100 flows through the, changes the flow on this line. It actually will add to the flow. There's all kinds of other flows going on, but adding 100 here, taking 100 out there, you will get a 15 megawatt change there. That's what that's for. By the way, this is what they use to help people decide if they can make a sale from here to here. They're supposed to decide how much they can do and do it safely, and they can say, well, this is 15 megawatts. If this thing was very close to its limit, 15 might overload it, and they wouldn't allow the sale. So it's a means of testing whether or not what the loadings are going to be on the system, and they literally make the maps. And for these, they make the numbers for the PTDFs for the entire continental US. Okay, now the LODF, different factor. I'll write it down again. LODF. It's a little simpler. Is simply equal to the change in flow L when line K goes out. Okay, so here's line L, and it's got an initial flow, and it's just got flow F sub L initially, and over here we have line K, and it has flow FK 0. Okay. What we want to know is if I drop this line, so if the circuit breaker's open on this line, then FK has to go someplace and it will flow around other lines of the system. What is the effect? So what is the effect on line L when K opens? And so the answer is like this: FL new, okay, is equal to FL original plus LODF LK times FK0. So you take the amount of megawatts flowing on this line and multiply it by this fraction. So here's an example. Let's say that this was originally 200 megawatts, and this thing was originally just flowing at 50, and the LODF was 0.6. So that said that when this line goes out, 60% of what was flowing adds to this flow. So FL new would equal the original, which is what, 50. That's 50 plus LODF, which is 0.6 times 200. So that's 6 times 6/10 is 120. So this is 120. Is that right? Yeah, that's 120 plus 50. This is equal to 170. So it jumps from 50 to 170. Now, if it has a limit that's below 170, then you've got a problem. This outage will cause an overload on this one. If this one has a limit of 500, well, okay, it goes from 50 to 170, no problem. So it's a very quick way to do this without inverting matrices or anything else to get these LODF factors. Later on, when we work on the problem, we're going to see that you can mix them. You can say, well, what's the flow? The rest of the problem I'm gonna leave to you. It's in the lecture. So what happens is, here's a line, and here's FL 0 flowing on the line. Here's K, FK. So this is line L, line K, and we have a sale going on from bus. We have delta P from bus I over here to bus J. He wants to sell to him. And the question comes up is, what is the effect on line L when a transaction is on from I to J, pardon me, of delta P, and line K is open. And so this would say I want to know if I can make the transfer from I to J and have a contingency on line K. Am I still going to overload that line? I'm going to let you look at the lecture and determine that should be in the notes, and we will pick that up in a little while. Let's see, we're due to start the problem session at 3:15. So I'll let you go to 3:50, maybe even 3:30. So I'll write this in the corner up here. Problem session, and it's labeled as problem session 3 on Thursday at 3:30 to give you time to work on that. Okay. These are very, very common techniques to study, and we don't ask you for all of the possible calculations, but there are calculations in there. Let me put I'm going to put that on a text message to everyone. How about that? Problem session 3, Thursday at 3:30 p.m. Okay, so now that's on the text. So we will see you at 3:30. Again, if you want to hit me with anything, let's see. I've got a question here. I watched the module Power System Security, but could you kindly explain, I hope I've done that, the use of LODFs in multiple line outages. Now I think what you mean is, what is the LODF if I have line 1 out and then I lose another line? So you might want to clear that. The truth is, we cannot use superposition. You can superimpose PTDFs, but you can't superimpose one line outage and then another line outage. That I know that can't be done. You're right. With any line flow, with any line, it will change flows on all remaining, including the other lines that are to be open. How can we use initial power flows to calculate post-contingency flow on specified line for multiple line outages? And the answer is, you have no way to do that. you have no way to do that. I am saying that, but in the back of my head, I'm thinking, if I dug and dug and dug in through IEEE power engineering papers, there may be somebody that figured it out, but I have a feeling that the formulas to do that. Think of this. So the LODF factors are as follows. You have a matrix that's big as the number of lines times the number of lines, because it's for each line outage. Each line outage has to have a factor to every other line except itself. The answer is, how much does a line outage affect itself? The LODF is -1. It simply says all of the flow goes away. So that gives you the correct answer. Now, if you want to do second outages, what we call double contingencies. So line X goes out, now line Y goes out on top of that. That would mean that I'd have to have a three-dimensional matrix. Each dimension is the number of lines. So the number of lines can be 10,000. So 10,000 times 10,000 times 10,000. Calculating such a matrix is just enormous, just enormous. Were I asked to do a study of, double line outages, I would do other techniques. I would not use LODFs. I would do other techniques. You could use LODFs to get the first set of flows, but then you're going to have to use some other technique. That's to the best of my knowledge. Now, that does not say that some PhD student someplace in the world has not studied this problem. But as I said, it's going to be 10,000 is 10 to the 4th, and I'd have to have 3 of those. That's 10 to the 12th numbers. That's a lot of calculation. That is a lot of calculation. If you could do it, if there were a formula that said, what's the effect on line X when line Y goes out and line Z? So there's three dimensions to that problem. That's a very good question. That's an excellent question. I tell you what, if you do find it, if you find such a paper where somebody has studied double line outages, let me know. Send me an email. Somebody should have posted my email there someplace. It's my last name, WOLLENBE. The University of Minnesota is too cheap to have more than 8 characters in front of the @ sign. So it's my name with the last 2 letters chopped off at umn.edu. Okay, if you find anything, send it to me. Okay, we'll see you at 3:30. Excellent question. Thank you. And I am going to switch the camera and We're back. I'm not sure I gave you the homework problem. Did you guys get the homework problem? Somebody text me or speak to me? I'm sorry. It just occurred to me that I may not have sent you the homework problem. I did send it to J-Ram about 3 minutes ago. Anybody listening out there? Yeah, he says it's uploaded now, but you couldn't have been very well working on the homework problem while you didn't have it. So that presents a problem. I'm really sorry. This course has been a little overwhelming for me, trying to get ready for the course and then get problems for the course, and that didn't get done in time, so I'm doing it piecemeal, and that's no good because as we saw here, we didn't get that ready for you. So the question is, do you want me to give you more time to work on that homework problem? I'm going to show you what it looks like. Make sure that you've got it. Here's the problem, and there's a table of PTDF factors and LODF factors here. And then there's some questions based on this network here. It's quite a bit of calculation. So I would like to know if you want to take some more time, if you want to take till 4 to work on this, please let me know.
I would rather let you do the homework, Professor, because it's getting late in the afternoon, so we can go home.
Okay, I'll just demonstrate it for you. So you do have this problem now. Okay, so we'll just I can also share this with you. And oh, by the way, generalized line outage distribution factors. This is in response to the question from who was this before? This was that's not going to do anything. They talk in this paper, and I think there is a better paper, and for some reason the IEEE doesn't recognize me anymore, and they won't let me get into, maybe because I'm now a life member and I'm not paying dues, they won't let me get papers. Anyway, there's this paper from, well, I don't know where I picked it up, but it came up okay. I will send this to, came out of Power. This is letters, so it's kind of short. Oh, it's a letter, and then maybe they don't care if I get these because they're short. But it talks about iterating solutions for multiple line outages. And there is another paper. So if you look up generalized line outage distribution factors, you can get to this paper. So there's the title there. Oh, let's do this thing again. We'll there's the title. Try entering that in the Google search thing, and you should come up with this paper and get it for yourself if you want. So I was wrong. People have done this, and they've done it, as you can see here, in May 2007. That shows that nobody ever asked, none of the students that took my classes ever thought of the multiple outages. So this was the This is the date on this right here. But I should be able to, I went to the IEEE, there's another paper which I think is a little easier to understand. I'm laughing because the second author is George Gross, a very close friend of mine. And I assume that the other fellows are students, although they're both members. I don't know where. Let's see. Whoop, I've still got that thing. I gotta clear it now. They don't. Goler and Gross are with EE Department, University of Illinois. Liu is with CRAI, Boston, Mass, whatever that is. I don't know. So this guy is working, and these guys are both at University of Illinois. And once I saw George Gross, he loves mathematics. He loves preciseness in notation. And just look at that. Oh, the other paper I think will be a little easier to understand. I'll try to get a copy of the other paper too. Anyway, so there's that paper, and I can, if you can't find it, let me know, and I will upload this to through Diagram. In fact, I can do that right now. I should be able to do that right now. Okay. Anyway, let's do this this problem. So here is the problem, and we've got the problem like this. Now I want to. Are you all hearing me? I'm gonna unshare.
Yes, sir. We do hear you.
You can hear me and you can see that, yeah. But you're looking at this, and I'm gonna. So when I share, does this just go away?
Yeah. Yes. It is either that or your computer screen, I think.
So right now,
you can see that
it's this computer screen.
Correct.
Okay. So I can go back and forth between them by just closing this.
Yeah.
We have this network, and very simple, 30 megawatts from each generator, 30 megawatts from each load. There's the data for the problem. Note the limits over here. Here's the flows. So the flows are, they all go from minus to plus the same, you know, from minus 35 plus 35, minus 25 plus 25, and so forth. Those are the flows on the system, and it calculates the percent loading here. And here are the LODF factors, okay? So I'm gonna switch back to the small camera, and notice that it says this is the buy and sell. So the PTDF from, let's say, from 1 to 3 on the fourth line. So that's I and that's J, and L equals 4. So the L equals 4 would be here. Now we're not using that in this particular problem, but it would be, here it is from 1 to 3. See, so this is the I and the J here, buy, sell, and there it is. There's the PTDF factor would be there, 0.29, so forth. Now in this problem, we're only concerned with the lines 1, 2, 1, 3, 1, 4. So there's the 3 lines. We're only interested in this line, and we're not interested in these other 2 down here. So the problem, we're only concerned, do any of these outages taken one at a time result in overloads, how much and what lines? So the answers are, so we're going to drop drop line, this is supposed to say line, line 1 to 3 results in an overload on line 1, 4. So we do this. Now, I wish I have no way to know if, let's try it. If I bring this close, you'll have to tell me if this works. I haven't, we lose the light. Do you lose the light there? Yeah, you do.
I can see you. I can see it very well.
Can you see it clearly?
Yes, sir.
Okay. So what we've got here is we've got the flow on 1 to 4 new is equal to the original plus LODF. Well, now we got to go back here and on the other page and look at the, we're doing LODFs. So I'm losing line 1 to 4. So this is the outage across here. So I'm going to lose, so this is the outage line here. So, and this is K, this is line K. And this is the monitored line down here. And we're going to look at the monitoring. I'm sorry, we're losing, the first thing says line 1, 3. So we really, this is K here, not this one. And I'm monitoring L is 1 to 4. And so there is the LODF, 0.14. So if we put the solution back in here, I'm gonna bend this. I wish there was a way anyway. There, so the original flow is 2366 on line 1 to 4, and 0.1467 LODF times the flow on 1 to 3, which is 1521, and that comes out to be 30 megawatts, which is beyond the limit of 25. So there's a contingency overload. If this one up here, if I drop 1 to 4, it results in an overload on line 3 to 4. So there's the same formula, only we're picking up the 3-4 flow and LODF. Now notice that the LODF for an outage of 1-4 onto 3-4. I want to look at this just a minute here. Why would it be if I drop this line that the LODF comes out to be 1.0? And it's really quite simple. And the reason is that if this line is out, whatever flow was coming down here is going to have to flow through the network and back on this line. So all of the line flow that was here gets picked up here. So that's a 1-to-1. All of that flow that you dropped out of here is going to end up adding onto this line. So it's going to cause an overload on 3-4. So there's also a contingency overload. Okay, now it asked you for the other outages, and I'm just giving you the overloads here. So that's, you know, which overload. The other lines don't cause any overload. Now it says B, the generator on bus 1 is going to reduce its output, and at the same time the load at bus 4 is going to reduce its load until there are no overloads due to lines listed in part A. How much should the load on bus 4 and the generation on bus 1 be reduced? So to come back here, he's going to do it from 1 to 4, right? He's going to bus 1 and bus 4. So he's going to reduce and reduce. Come on. Reduce load and reduce generation here. Now that says to us that you're really putting in a delta that's negative, okay, if you're reducing. So here's the line 1014 overload that we calculated the flow after the transaction. So this is the PTDF. So this gives us the new flow after the transaction. That's what that says in that superscript up there. It says after transaction. I wrote these with there's a program called MathType, and you can get it, and it just provides a way of getting very, very complex equations in Microsoft Word. But it allows you to get some extremely small font. My eyes are getting to the point at my age where I can't hardly read them. But anyway, after the transactions, that it's the original flow plus the PTDF for this flow. Now, then it says the final flow, okay, is the flow after the transaction. So what we have to do is we have to put this numbers right into this thing, and then LODF. This is the flow after transaction on 1,4, and this is the flow. The term in the brackets. Let me make that clear. And this is the flow after the transaction